Welcome to episode 8 of the Fractal Cosmos. I'm going to just say a few brief words about mechanics in the Fractal Cosmos. And of course, this brings us to the subject of relativity. Now, as you know, relativity in its early days resolved the problem of the ether. This was the luminiferous ether through which waves of light traveled. This was considered to be some kind of fluid, and the Michelson-Morley experiment said there is no fluid, because no matter what direction the Earth is traveling and no matter how we measure this light, we always come up with the same velocity, so there's no retardation of the velocity of light due to the direction and motion of the source of the light. So Lorentz and then Einstein resolved this problem with the Lorentz transformations. And Einstein put this in a very elegant formulation that is very compatible with Maxwell's equations and had a kind of symmetry that physicists admire in their mathematics. However, Einstein approached this problem by making two postulates, and then he found out it matched the experiment pretty well. These postulates of relativity are well known. I think it's the speed of light is a constant, and the physical properties are the same no matter the frame of reference. Now, some of you who have read some about relativity and read how the ether is forbidden or superfluous at best, may be a little alarmed. But the fact of the matter is, there's nothing wrong with having space being filled with energy. This is the viewpoint of quantum field theory today, with the quantum vacuum. Particles are appearing and disappearing all the time in this substrate of energy. This is the Dirac theory of the electron. So in modern physics today, this ether is not really forbidden, although they don't like to call it ether because it gets mixed up with 19th century various kinds of soups, we can call them. Now, if we're looking at these particles and how they behave when subjected to a force and acceleration, you can observe that these particles have built-in rulers and built-in clocks. Okay, they have radius r0, which is the core, and each shell is at a certain distance. The nodes are at distances of r0, 3, r0, 5, r0, and so forth. Now, as you start to accelerate one of these particles, the way that the inertia is held up in the particle is carried by a circulation of energy around the particle, and this brings about a contraction, and you can actually show in the equations how much this contraction would be. And it also brings about a slower period of vibration. So these bizarre results that come out of the Lorentz transformation, namely time dilation and length contraction, are a natural consequence of the three-dimensional standing wave nature of the atoms, with the frequency of vibration determined largely by the frequency of light. See, these waves travel at the speed of light that surround the atom. So this is very hand wavy. However, you can look at one of my papers called Mechanics in a Fractal Cosmos, or Fractal Mechanics, with notes on relativity, relativistic mechanics in the Fractal Cosmos. One of the papers on fractalcosmos.com covers this very succinctly, I think very elegantly, because we're in a unique position here of being able to measure time and length by the particle itself, which is in motion. And out of this, you'll see that the speed of light is measured as a constant based on the changing clock and changing length of moving source, or the observer. Very elegant. I struggled with this for many, many years until this solution popped out. My father mentioned that it wasn't a problem. Special relativity is not a problem. Interestingly, you also get an increase of mass. So you can look at what is mass in terms of inertia, rest mass, so on and so forth in terms of these fractal particles. Gravity is another matter. That's also determined by the core and the shells of standing waves surrounding this core, and we can take up gravity another time. But that's in another paper on fractalcosmos.com, and also in my father's original treatise. You can see how gravity is treated. Results don't exactly agree with general relativity. General relativity is a very beautiful theory relating the curvature of space, is what it's called, but it doesn't really give a phenomenological, it doesn't actually show the mechanics of why it works. It describes gravity very nicely mathematically, but what exactly is meant by curved space, and that this curved space affects the motion of mass. There is a mechanism for gravity, and it's wrapped up in the changing radius of these atoms over time. That's why the force of gravity is so much smaller than the force of electric field, of the electromagnetic force, the interaction of charge. Gravity and charge are very different phenomena, and the reason is that gravity depends upon the ever-decreasing size of the atoms, in which the energy between any pair of atoms dissipates at a different rate than the energy around them, and so there's an attractive force. It's a very interesting theory, worth looking into. Resolves the many age-old problems of where does gravity come from. So I'll leave it with that. Take a look at the papers online and come to your own conclusion about these matters. And we certainly could use some better formulation mathematically of these concepts. Thank you.